Yeah, hello everyone. It's our pleasure to have Yuxuan here to share about his recent work on scalable quantum dynamic compilation via quantum machine learning. And in this work is pretty in kind of like interested to me because I like they utilize the so-called out of generalized distribution to basically characterize data. I think it's like this one that they have a larger scales of experiment to trying to validate ideas and also consider tensor network, so which will be very interesting. I think like Yuxuan will be able to tell us more about it. Yuxuan, the floor is yours.
Yeah, thanks for the introduction, Pengyi. And my name is Yuxuan. I'm currently a postdoc based at Vector Institute at University of Toronto. I recently just finished my PhD and from UT Austin, where I was advised by Scott Aronson and Andrew Potter. And my current research and also the theme of the research in our group is a intersection between two of the most promising computational models, namely quantum computing and artificial intelligence. Now, there are a bunch of interesting questions you could ask in between these two computational models, such as how do we use quantum computers to speed up artificial intelligence or machine learning training, or how do we use artificial intelligence to better design a quantum computer? And the second direction here is the focus of this work. So the motivation of having a quantum computer can be traced back to Richard Feynman. As many of you know, this famous quote, nature isn't classical, and if you were to make simulation of nature, you better make it quantum mechanical. So that's why we want to build a quantum computer. And in the past few decades, effortlessly investigation by theorists in computer science and physics, we found problems that are out of physics that are also interestingly easy to be solved by a quantum computer, and that are hard for what we believe for a classical computer. These problems, are usually coined as a term, so-called quantum supremacy. That is, namely, we ask the question whether a quantum computer can outperform a supercomputer, such as one of the best supercomputer we have, such as Frontier, in performing certain given tasks. However, in practice, we found this really challenging. In 2019, Google published this quantum supremacy paper, which really opened a serious tug of war. There's a bit of back and forth between, people who are supporting quantum supremacy and, and numerical people who want to spoof these quantum supremacy tests. Mostly like, so initially these tests could be, sampling a Haar distribution that's natural to quantum mechanics. And, later we have more demonstrations exemplified by, for example, IBM or, D-Wave, such as, simulating quantum dynamics and spin glasses. So, so it is our belief that, however, at current stage, if we were to compare the hardware design for quantum computers to classical computers, we are still in the stage of vacuum tubes. Namely, we don't have a fault-tolerant machine, and we don't know if we were ever going to have a transistor analog of quantum computer. So it is then natural to ask the question that, how to best use machine learning to improve quantum computer designs. Namely, how do we use machine learning tools to minimize the quantum resources that we use to execute a certain operation. And this task is also known as a quantum circuit compilation problem. So on the right here, I printed out a quantum circuit using Qiskit. And each boxes here is a quantum gate. As you know, I believe many of you are familiar with. And on the bottom, I have two quantum circuits and C2. So actually one, let's say the matrices, and you do multiplications, you can find C1 is equivalent to C2. So since we cannot like give just 1 2 to the n by 2 to the n unitary as an input to the quantum device, and the quantum device really relies on what is called a universal gate set that is usually consists of merely single qubit gates and 2 qubit gates. There exists a lot of rewrites or equivalent representations that we can find for the same quantum execution or operation. And as we just said, quantum gates are known to be noisy and expensive. And how do we find the ones with a smaller number of gates? Or in some instances, we want to minimize the circuit depth. And in other instances, we might also want to minimize the use of non-local gates, for example. I should also mention that this talk is meant to be interactive. So if you see a problem, just stop me at any time. Okay, so in this talk, or in this work, we focus in particularly, what was first envisioned by Richard Feynman, namely the task of simulating quantum dynamics. So the goal is such that we give a input, a description of a quantum operation U. We want to find a so we could use a parameterized quantum circuit V that consists of, for example, these brick wall circuits to use as few gates as possible to represent this operation. And in particularly, we set U to be generated by some Hamiltonian, some physical Hamiltonian. In particular, we consider both 1D and 2D Hamiltonians in this work. And we compare the results to the good old, Trotterization result. That is, you write down the generators of the Hamiltonian, you break the Hamiltonian into non-commuting parts, and you use, for example, BCH theorem to write it as a decomposition of local gates, right? So that is widely used method. However, it is also known to be non-optimal by a series of, excuse me, a numerical and analytical study. So, for example, I think Andrew Chels has a paper saying that if you randomly permute the orders in the Trotterization, then there's a good chance that you actually get a better Trotterization than the one you developed. So that's like one evidence of Trotterization being non-optimal. And also, if you view the evolution of Hamiltonian as a walk in the Hilbert space, then there could be a shortcut between the 2 points, the initial point and the end point of such quantum walk. Namely, the Hamiltonian, the time evolution generated by Hamiltonian could be non-optimal in some sense. So our task is to use these variational quantum circuits as a tool to probe this shortcut. So early VQC works already found that, the those variational quantum compilation methods could give, results that outperforms a trotterization. However, their study were really limited to smaller system sizes. And here is why. So the main challenge of a variational quantum compilation method is to compute the cost function. So the most naive cost function one could come up with is, of course, the fidelity between the target the target unitary generated by a Hamiltonian dynamics and your variational quantum circuit V. So on the top, I have a sort of tensor network representation here for the trace distance between U and V. This is basically if you were to view U as like a representation of a dynamics, a dynamical process, this could be given in the form of a very finely trotterized circuit. If you don't want to write down the really dense 2 to the n by 2 to the n full matrix representation. And V, on the other hand, is the variational circuit that we mentioned here that depends on the theta that we vary over. So this is the most naive cost function that one could write down. So, in order to compute this overlap, on a quantum computer, we have to use something called the Hilbert-Schmidt test, which you could think of it as preparing 2 copies of the system. And, on the one part, you apply U dagger. On the other half of the system, you apply V. And then you create these entangled EPR pairs between your prime and due system and do a projective measurement. And this cost function is also non-ideal to be computed because even though this doesn't involve, evaluating the trace distance between 2 very large matrices, these entangling operations, as you can see, creates these long-range interactions that is very costly to be simulated using standard numerical techniques. So as such, in conclusion, these previous studies have generally been limited by their system sizes and topology of these models. Now, many of the more recent papers try to get away of this by using local cost functions. However, these were not also sort of, you could say that it works in certain scenarios. However, the general idea was that it's also generally hard to generalize to a deeper circuit where the locality would fail, because usually this requires tracing back only to some part of the circuits that is within some light cone. So then we ask a question here in this work: how do we use machine learning to help? Can the idea of using data of instead of writing down the full unitary representation, can we use the idea of learning? So, okay.
Sorry, I have a question.
Yes. Mm-hmm.
Sorry, Yuxuan, I have a question over here. I just want to clarify, like, what do you mean by topology over here?
So here I just mean the geometry of the model or the interaction graph, the interaction topology. For
right,
example, so they were yeah.
So go ahead.
So as far as I could tell, most of the previous works were focused on 1D interactions, for example. And 1D we have like very good numerical tools anyway. So yeah, we think it's the most interesting if we can go beyond the 1D limit, right?
Right. So it's basically can imagine Ising Hamiltonians, and then by topology just like
Yeah.
1D, and then the graph over there is just like connected linearly, and then like now we basically go beyond that to consider 2D topologies in the task and in your numerics
Yeah.
and study, right? So this is what you mean by topology. So it's a topology of the Hamiltonian in terms of their interactions.
Yes,
Okay.
yes, yes. Or
Okay,
I
okay.
should say geometry of the model, or
Geometry of
yeah.
the graph associated to the Hamiltonian.
Yes, yes, that's right. That's right.
Okay.
Yeah.
Okay. Right. I see. Okay. Yeah. Thanks for that.
Yeah. Well, it also matters because for you might think at a glance that this shouldn't matter that much, but it actually matters because for like for example some Hamiltonian, if this were all-to-all connected, then you definitely need a denser V or like a deeper V to approximate the dynamics, right? So the
Okay.
numerical computation there becomes really hard. Yeah. Okay. So now we make use of the recent progress in quantum learning and cast the compilation problem as a quantum learning problem. So let me remind you, the original task is such that I give you a quantum process Q, and you want to find the accurate approximation that use as few gates as possible. So equivalently, we could think of this as a learning problem that, a quantum learner V now wants to obtain a accurate description of some U that is secretly prepared by some experimentalists. Now the learner V is allowed to make queries to U by inputting certain samples from a distribution of quantum state that he or she chooses. And in return, the experimentalist would prepare the interaction of V and act it on the initial state prepared by the learner and returns the state after U times the initial state, right? And then we ask what distribution can we use and how many samples do we need for this learning process? I guess there are two main challenges in consider machine learning for quantum in general. So first challenge is that unlike large language models, where we could have a huge amount of data set, quantum data is still expensive due to the fact that we still lack a fault-tolerant quantum computer. We only have, quantum computers with merely dozens of qubits, or the noisy ones might go up to hundreds. But still, it's hard to obtain. And if you ever executed a real experiment, you could understand that it's also very expensive to produce the data. And the second challenge is that we would like these samples to be generated efficiently. So let's say if you could sample efficiently learn U, but for example, if this were to require a quantum state that is of polynomial depths to prepare, then this whole process doesn't quite make sense because it is hard to prepare a polynomial depth quantum circuit either on the noisy quantum computer we have nowadays, nor numerically you could do neither of this, right? So these are two main challenges that we're gonna see to be resolved here. So let me just throw a little bit formalism here. So in a real experiment, the learner V could only obtain a finite number of samples to estimate this so-called expected risk. So let's first consider this following imperial risk function that is designed as the following. So basically, so looking at this equation is such that you sample from a distribution Q, and you sample n sample times to form a data set D of Q with respect to this distribution Q. So it is not very hard to see that when Q equals to the global Haar distribution, right? Meaning that if we were to pool every state as a Haar random state, then this evaluation in the limits where you evaluate infinite times, meaning you sample meaning the number of samples goes to infinity, this would reduce to the trace distance between U and V. Is that easy to see? This is almost like you if you're allowed to take a snapshot in every single direction in the Haar random basis, and you're allowed to snapshot the overlap between V and U and V in infinite times, right? Then it is for sure that you obtain a estimation of the trace distance between the two. Okay, so the cost function here, however, as we said, is still prohibitive to evaluate, since Haar random states in general is of high complexity, is of exponential complexity, as one could prove, with overwhelmingly high probability. So this isn't very practical in practice, neither in real experiments nor in a numerical simulation. However, we could reduce this cost function to something much simpler via this so-called out-of-distribution generalization. So the idea we use here is that if we train the learner on one set of data samples, the out-of-distribution generalization theorem says that we could transfer that learning into another distribution. Namely, here we pick, so we want to train this model on some easily preparable distribution. And then the theorem guarantees that the performance of the learner is also good on a hard distribution. Namely, here is the Haar random distribution. Okay, so instead of training on a Haar n distribution, you can notice a slight difference here. We use Q to the Q equals to S Haar1 to the n, which means which is namely the ensemble of random product states. So namely, the samples could just be obtained from sampling a random product state distribution. Okay, so this results given by these people, Carlo Huang et al. They showed that if you do this, then you're guaranteed that the risk, the imperial risk you get from a Haar1, namely the random product state ensemble, is bounded by 1/2 of the Haar n ensemble, like the true Haar random ensemble. Namely, in return you get a bound for the true unitary infidelity. Is this part clear?
What is and the big
Yeah,
N?
yeah, the big N. The big N is 2 to the small n. So this is
Sorry?
you should think of this as just 1. The big N is 2 to the small n, which is this
Okay.
factor here is just 1 in larger limits, for example.
I see. It's 2 to the small N.
Yeah, yeah, yeah.
Dimension of the system size, right?
Yeah, it's a degree of freedom in the system, for example.
Okay. Okay.
Yeah.
Data. Yeah, it should be clear over. And this one is the expected risk, right? It's not okay, empirical. Okay, I see.
Yeah. So in terms of like if you want to sort of visualize this process, this is just a learner feeding in the experimentalist with product states, random product states that he samples, and then in return the experimentalist prepares psi I times u dagger, and and then the learner could contract it with his or her own copy, namely the v times psi I, and compute the overlap between the two, right?
Okay.
And use this as a cost function. Okay. So the other question we threw out away was how many samples do we actually need, right? So actually, I'm skipping a lot of analytical study here, but if you do the math correctly, the learning theorem also guarantees that if the quantum circuit that you were to learn is of a shallow depth, or in other words, is of a low circuit complexity, then you actually don't need that many number of samples. So you can see this error is bounded by this older square root t log t over ns, wherever t refers to the number of parameters in your parameterized quantum circuit. This means that roughly the number if you fix the learning error, right, then roughly the number of samples you need is linear, grows linearly with system size, or rather with a circuit volume of V. Okay, and here we show some numerical results here. As you can see that this is, I believe, testing on some transversal field Ising model in 1D. And we were able to go to quite large system size with techniques I'll mention in a moment. We conducted this on 80 qubits and total evolution time of 0.5. The trend you can see that here is the training loss here, and the test loss here has a gap. So if you follow the same color, you can see that when you only use one sample, like there's no way we get this estimation right? So, and if you increase the number of samples to roughly 16, you see a very small gap between the training loss and the test loss, for example. And to us, we think it's quite remarkable that even at this large system size, and you could still train the PQC with a relatively low number of samples, namely 16 here.
So for the testing, are you using the global Haar or local Haar?
So here I believe we are doing in distribution generalization, meaning meaning the local Haar. However, if you generalize to global Haar, they differ by at most like a factor of 2 or something.
Okay.
So yeah, you should think of like the bounds of the global Haar is like twice of the dashed line here. Yeah. So rough. So for example, instead of 10 to the minus 4, the bound, the lower bound, sorry, the lower or upper, the upper bound of the learning loss is like for the test loss of the global Haar could be 2 times 10 to the minus 4, something like that.
Okay.
Yeah. So we did test for both, but there's a theoretical guarantee. And numerically, actually, I haven't shown here, but we found in the paper that this factor of 2 isn't quite tight. We found it's closer to 1 rather than 2 in practice. So the local Haar loss from what we see is very close to the global Haar loss in the testing cases, right? And yeah, I believe we have a plot in the paper, and yeah. Okay, so yeah, let's
Actually,
have
how long?
a summary of yes. Yes,
Yeah,
yes,
over
yes.
here, classical simulation, right? How long does it take for you to kind of complete the graph, for example? Like how long does it take for you to do the optimization?
This one.
Yeah, because at the
This.
it's yeah,
Mhm.
it's pretty large, right?
Yeah. So actually, this one you can do on a laptop in like maybe an hour or two. Yeah,
Oh, okay. Hmm.
yeah,
That's
yeah,
very
yeah, yeah. If you use cluster, you could go to like much
mid.
larger system sizes and times.
I see. Okay.
Yeah, it's yeah not that very it's not very costly. Uh,
Okay.
yeah. So the trick we do here, so there's 3 steps, right? So as we can see from this plot, your new cost function is namely a linear sum of these estimations of your risks that consists of n samples. So for each of these costs, we compute the generation of data here with a TBD algorithm. Namely, we act U on this product state psi I with these MPS methods. So namely, you can think of this as a MPS compression of the time evolved state. I'll give you a little bit background or slash review of the MPS method in a second. But yeah, what we found in numerically is that if you do this compression classically, it really saves a lot of computational resources. And I think that is the key to this, trick. That is, you're now allowed to do these MPS compressions, and in return, you get your training much faster done. So okay. On the other hand, we also generate these predictions using this PQC. So here we actually so for the update rules of V, namely the parameterized quantum circuit, we use Atom and the global update. Okay, now you could think of using other methods such as like a SVD solver, for example, just as like in DMRG, you solve for local SVDs, and we did found that it's less, that is in a way faster, but give you less optimized, less accurate results in the end, because these local update really lacks this like ability of searching for a global path or something like that. Yeah, so in general, this TBD could be conducted efficiently for short times, both in 1D and 2D. So by 2D here I really mean quasi 1D, right? Like if this were a real 2D system, then yeah, the TBD would fail. But for quasi 1D, namely if you consider like a 2D stripe, this could be efficient for T up to log n, for example. I'm just gonna quickly flash you through the matrix product state method. For any wave function that one could consider, you can consider this the bipartiting the wave function into two parts, namely the left part of the let's consider like a qubit spin chain. You can bipart it in the middle, cut it through in the middle, and consider like now the system is Schmidt decomposed into two parts, and namely you do a QR decomposition in the in these weights, right? And for these Schmidt weights, a lot of the times you find these like Schmidt weights would decay exponentially for physical states, such as ground state of locally interacting Hamiltonians. So you could toss away a lot of these like Schmidt weights. Yeah, and if you were to sequentially perform this for a n-qubit system, you get this so-called matrix product state representation. So a TBD is merely you perform the time evolution as a very dense trotterization to your initial state, and each layer of gates you apply and you perform this SVD, and in the end you could compress this time evolved state that we in this data generation stage efficiently. Okay. So for 2D systems, we do a quasi 1D treatment. Namely, we use like a snake zigzag indexing for these like quasi 1D systems, and treat it as like treat the let's say the vertical interactions as sort of like the long range interaction terms. So let me now show you some results, comparisons to trotterization, as I promised you. They should, we should ensure that we're comparing to a fairly good trotterization, right? Because there certainly exist many different let's say algorithms for trotterization. And here we use a recently published paper where they optimize for these like different trotterization orders, and they optimize for the trotterization factors such that the leading factor of this trotterization, the leading terms in the error in the trotterization could be minimized. Right. So P here represents the order of trotterization. These little stars are the trotterization results that we compare with. So this red line, on the other hand, is what we found through this quantum machine learning trained VQCs. And P here represents the order of trotterization, namely the asymptotically the error of a P order trotterization would grow as P to the N to the P plus 1, something like that. So if we were compare this is tested on some eigenmodel with some self-do interaction, some next nearest neighbor interaction if kappa was turned up. You know, if there's no kappa, then you just have a transverse field as a model with some like longitudinal interaction term. And comparing, like looking at both diagrams on the left and right, we can see that, you know, you can see the stars is really far away from the red line. And in the same resource comparison, let's see, maybe focus on 10 to the 3 C0 count. By the way, we train each gate as a SU4 gate, namely each we treat the VQC like the little blocks is in the VQC. We treat each parameter as a free parameter, and we do like QR decompilations to ensure unitarity. But in return for fair comparison, we would all compare them in the C0 count. Yeah, to ensure like fairness, right? So for the same C0 count, we could see that, you know, we get like 10 to the -5 with these quantum machine learning VQCs, whereas the best known trotterization on this Hamiltonian could only do like 10 to the -2. So it's a vast improvement in my opinion. And like on the other hand, looking at this I think model with next nearest neighbor interaction, if we were compare the p equal to 6 with the VQC result, we find that, you know, on the same accuracy, you actually get like, let's say, you get to save maybe a factor of 5 or something on the C0 count. These are both trained on very few samples, I believe. An S equals to roughly 16, and you can probably get better accuracy if you increase the number of samples. However, already here compared to trotterization, we get like, you know, much better results. So one could also test these in long time limits. Namely, you train them for, you know, for like a time slice that is roughly t equals to 1 or t equals to 0.5, and you test the long time generalization. So here we consider a MBL Hamiltonian, namely a disordered Heisenberg model. So, you know, the first term is just a good old Heisenberg model, and we also add these disorders to it. Namely, we randomly pull these HIs from -h to h, and add these disorders to the model. Okay, and you can see that when h is turned up, you get a many-body localization, and the spins charges would not propagate far away from the initial activation position. On the other hand, you do see these ballistics propagation of charges in this ballistic diffusion of charge in this Heisenberg model, and we compare both to a very fine TBD for these like long time limits. And we also compare this in 2D. We also train these models in 2D. Here you can see a 2D Heisenberg model, or you may also call it quite a 1D. It's a 3 by 21 square lattice. And here what we do is we activate the middle sides. So we return them to be spin 1. And we do like a quantum quench. We time evolve with this learned Hamiltonian for up to t equals to 2. I believe the time slice we trained here was like 0.2 or something. Yeah, we just repetitively this circuit for roughly 10 times to get the t equals to 2 result. Yeah, you can see a diffusion, like a meltdown of the initially kicked charges. And here, like at t goes 2, the system is roughly agnostic of excuse me, the initial state in some sense in the position basis. Whereas in the momentum basis, it builds these localized waves. So, okay, there's some other results that I haven't mentioned in this talk due to limitation of time. We also, in order to train this large quantum circuit, we also had to fight these like Fermi plateau issues. So we basically designed 3 different types of warm start methods. We compare them, and some of them work slightly better in certain scenarios. And yeah, you can find these details in the appendices of our paper. And we also considered, learning a Hamiltonian with U1 symmetry in a specific charge sector, right? So if we now think of the XXC model, for example, and we focus on the action of that Hamiltonian in the half-filling charge sector, for example. So naively, you may think that if we train that charge sector, it should be much easier because you're only focusing on a certain block of the Hamiltonian, of the unitary generated by that Hamiltonian. However, we've actually found that when data is drawn from a single charge sector, this generalization actually fails. Yeah, we can see this from the right. When we trained this XXC model on a U1 conserving charge sector, namely we train them on, say all product states preserve a certain Hamming weight. The generalization is actually not very good, even within that charge sector, as compared to a random product state. And then I think we have a analytical understanding of this. And it's interesting to see, how symmetries would affect this quantum learning process, for example. We also, as I briefly mentioned, compare local updates to global updates. And these global updates have showed a better performance. So what have we learned here? I guess the main takeaway point of this talk is that the idea of thinking of quantum physics in terms of data could be powerful. Even though the Hilbert space is vast, even though it seems like this 2 to the n degree of quantum freedom is it's a little bit hopeless to be represented. Maybe we don't need a full description of the system. We don't need a full description, of these unitaries. And then maybe data is all you need, as we found in this, like, in the success of large language models, for example. And, one immediate practical application here is to use this compilation method, not only for optimizing certain Hamiltonians, but also for a certain geometry of a hardware, such as these IBM quantum machines, coming with these hexagon-shaped qubit layouts, and ask how many gates can this compilation method save us. And in one recent follow-up works, here at ETH with my colleagues, we also find analytical tools that could further reduce the number of variational parameters using this like Pauli propagating method that we will hopefully have more to say about soon. And I do want to thank you for your attention, and I want to thank my collaborators. They're my amazing mentors and friends, and without them, this could not have been accomplished. Yeah, thanks again for your attention.
Yeah, thanks, Yuxuan, for the very interesting talks, and it's like your results are very interesting. So for the audience, if you have any questions, feel free to unmute yourself to ask the questions or type a question in the chat, and I could probably ask about it. In the meantime, I think I could ask a couple of questions. Over here, I think all the training and testing are done classically, right? Just like you didn't involve any quantum. Am I correct to say that?
Yes. You, in principle, you could do this training process on the quantum machine. However, here mainly we consider this as a classical algorithm.
Right.
Yeah, here.
So over here, you
quantum,
didn't really care about quantum. Sorry, go ahead. Please go ahead.
Because quantum machine we have so far is quite noisy and like generally it's even hard to do the VQE process on a quantum device to a large scale. So requires a lot of gradient estimation and which is something. I mean, in principle, this could be done on a fault-tolerant machine, right? And that's the ultimate hope. Yeah.
So over here, it's just like not concerning with all the like hard to classically simulate things, and then you just see, okay, for a given Hamiltonian, you want to understand the property, so you use tensor network to do compilations and trying to make predictions based on that, right?
Yeah. That's right. Yeah.
Okay. And a lot of questions over here is that you are using our general distributions, right? And have you kind of do the testing on the global Haar? Because I believe the global Haar would be very hard to represent in terms of the tensor network, and so for classical simulation, hard, right?
Yeah, that's right. That's definitely one of the challenges. Like even though we haven't tested like some of the largest systems on global Haar, we were able to test some of the smaller systems to just as a sanity check. So I think we were able to test like something like if this were Ising model, then something like 40 qubits or another trick one might be make use of is to write the like the time evolution operator here, U dagger as an MPO, and then the contraction could be faster. But also, you could argue that you're losing some information there as well. And the MPO of these 2D systems are generally hard to be written down.
I see. Sorry, can I interrupt here? Yeah, that's actually what I wanted to clarify here. When you do TBD here, whether you actually, as you said, do any kind of approximation. So as it sounds like, at least for this work, this TBD process, at least this the when you're doing it here, it's not, there is no approximation. You don't, you do not take like the highest weights components operators only.
There is some approximation, but we set the cutoff to be something SVD cutoff to be like 10 to the minus 12 or something.
So basically keeping the whole. I see. Right, so you're basically keeping the full as much information, essentially the full information. You're not really truncating any.
Yeah. That's right.
Of course, as you mentioned, you could make it more efficient by just having a larger cutoff for faster simulation, but then you might do some accuracy.
Yeah, that's right. Yeah.
Oh yeah, can I ask some questions? Sorry, I don't know, Bing, if you are done.
Yeah, sure. Yeah.
Just go ask a question you feel like have any.
Okay, yeah. So I think I have a couple of questions. One is I don't know if I missed this, but did you discuss or describe the architecture of this variational ansatz that you're using? Is it a quantum circuit based?
It's like this brick wall circuit.
Yeah, it is for each of these two qubit blocks. Are they? Is it a general SU4 unitary or what is?
It's a general SU4 gate. Yeah.
So it should be parameterized by a few parameters, or how does it? Do you have a specific decomposition for it? Or,
yeah. So basically, we don't do decomposition because that's what we found is that it's easier to encode on Torch that each block as just like a block with all of the indices being free parameters, and then you do a QR decomposition of the wave function to normalize the weight to ensure you each step before evaluating the loss function, you do like a QR decomposition. You isometrize all of the gates. So instead of considering the SU4 gates being written down in this, what's it called, the carton decomposition or something like that. We don't write down as like 3 C0 gates and then a bunch of single rotations. We don't do that yet. We just treat this as like one tensor. Each entry is a free parameter, and then we normalize. We do a QR decomposition before we evaluate the cost function this time. So that way we found more efficient.
Right. So I see. So it's more like how should I put it? So the weights, what exactly when you train the weights? So let's say in the end you have your answer, then the weights actually correspond to what again? So normally in the PQC, the weights would be, for example, the angles that enter some gate, right? For in this case, as what you describe, it doesn't sound like that's what it is. It sounds like it's like the
the way it suggests, each single entry in the SU4 gate, right? You have 15 free parameters.
Yeah,
and these are the weights. Yeah.
Oh, okay. So there will be the coefficients of each of these 15.
Yeah. It's like a dense representation of the SU4 instead of like we don't do some people do like layers of RZs and then
that's right.
You got C0s and RZs. So each of this is like a SU4.
Oh, okay. So it's basically essentially I can think of it as the coefficients for the 15 basis let's say operators in the SU4 space.
Yeah, like the whole matrix is basically all consists of these like free parameters if you want.
Okay. Yeah. Sure.
And so if you do that, the matrix is not guaranteed to be a unitary, right? So we have to do like a QR decomposition in the end and normalize the whole tensor network.
Right.
Yeah. So we rescale the weights. Yeah.
Okay. Yeah. Thanks. So the other question I have was about the number of samples. So you mentioned like few samples, like earlier you had a plot showing the scale with respect to the accuracy with respect to the samples. And does that scale with system size or
that's a very good question. So what we found is that if you consider like a periodic boundary condition, for example, and if you consider all of the circuit parameters to be set to be the same on one single layer, right? Then it actually does not grow with the system size. It only grows with the system depth. So that's also one.
You mean how long is it?
Yeah. That's right. Yeah. You can see here T is the total number of variational parameters. So it really breaks down that how T is compared to NS. So usually for non-translational invariant systems, T would grow with like system mass, right? Namely the system size. However, if there's translational invariance, then what matters is the depth of the system.
Right, I see. Because you're using translational invariance, then your variational answer essentially you're built into it also translational invariance in it, so you don't have I see.
So having few parameter helps here, and we actually had some numerical evidence that, so if you were set, so this I think is a open boundary condition, but like if you consider like a periodic chain, or even some scenarios, like if you consider a open boundary chain, and you consider all of the parameters to be set to be the same, then you could, get a better training. The converge is faster, meaning the gaps between the train and test, they converge faster.
I see. Okay. Yeah, thanks a lot for your clarification.
Yeah, no worries. Yeah.
Right. Okay. Maybe I just like one last question before we end the seminar. Over here, basically, you propose different kind of warm start solutions, right? And then you basically show the curve for the how the cost function evolve. Like, do you calculate the variance of the gradients or something like that? Do you do that? Because it's how we kind of like see whether there's barn plateaus, right?
I see. So yeah, so what we found in practice is like if we boost this so okay, yeah, maybe like, so there's a recent paper, right, saying that basically if you do the warm start like sequentially, then you're searching in the sub manifold of the parameter space that is always barn plateau free. So that's also what we sort of find in this work. Like if you give a kick in the start, like if you just feed, for example, the trotterization circuit as the initial start, as a warm start, for example, and that already ensures that you're searching in a ballpark that's sort of barn plateau free. Yeah. So what we found, I guess, in short, in the end, is if you boost the algorithm with like enough signal, then it doesn't matter what kind of warm start you would actually use. But yeah, I do agree that it's interesting to look at the variances. Yeah.
Right.
And then have a more systematic study on that. Yeah.
Right. But I think it's like I think the main novelty of this work is not really on the barn plateau. That one is just as a kind of like extra things that provided to the papers. I think the main kind of like goal of the paper is really on the tensor network and trying to do the training and see how well we do. But actually there's also kind of a related question over here because you are looking at barn plateaus, right? But are you concerned with the local minima and things? But it seems like over here you are doing pretty well, so I'm not too sure whether there's of concern or not. Yeah. Yeah, as in that would definitely out of like the scope, but I'm just like curious how what's your thought on that?
Sorry, could you repeat the question? Like,
yeah, because like for variational, right, typically we have two phenomenons. One is barn plateaus, right? The other one will be kind of have a lot of local minimum because the landscape is not convex, right? Because we parameterize it, and then basically if you plot out the landscape in terms of the x-axis for the data, then you can see there are a lot of local minimum with that, and that would be an issue for the optimizations, right? So I'm wondering whether there's same issue for you guys, or is fine, or like do you kind of like have a moment of thought, okay, whether it's like there's a local minimum or global minimum. But in terms of the result, it seems to be a very nice one. But I'm not too sure about for example, there was one plot that you show that when you have the symmetry, basically the generalization is bad, right?
This one.
So is it no.
This one.
Yeah.
This one.
Yeah, this one. So would it be because of its local minimum, it just like doesn't optimize very well, or yeah, I'm not too sure. I'm just like saying what I'm thinking now. Yeah.
Yeah. So the training of this. it's actually very good. If you look at the training loss of this, it's actually very good. It's very comparable to the product state training loss. However, the generalization loss is it's like very far away. I think this is because like it's very hard to generate like a unbiased sample within like certain charge sector, right? For example, like let's say all charge with having weight 1, this would be already W state, which require like a deep circuit repair. So yeah, I guess the idea here is the dynamics of this, like for example all having weight 1 chart like initial states, it's very different. Like you could imagine performing a evolution of such state with like 1 0 0 0 0 initial state, and then 0 0 0 0 0 1 initial state, and these two would give you like very different dynamics. So yeah, I think it's just the natural sort of like a natural bottleneck of the fact that we are considering these like symmetries.
Right.
Yeah.
Right. So this one is
Instead
the
of
physical.
a local minima.
Right.
Yeah. This one has some physical reason.
I see. Okay,
so
maybe not about this.
So
like in general, how's the local minimal things played out
but yeah, I do agree. Like for example, the phenomena I see here, right? Like eventually this plateaus to like 10 to the -5. Like on the right, we haven't seen it's like plateau yet, but on the left we can see this like the slope being sort of like flat and yeah, I think this is like a question basically for all gradient based search. We also see like similar yeah
I see.
like
I think
this could be a sign of yeah.
it's pretty hard to tell whether it's local minima, and it's because it's also hard to do analytics on that as well. But in any case, I think it's like all the results that you shows are very promising and seems to be a nice algorithm for us to use to probe the physics using some cheap like simulation methods that's provided in your paper. So I think it's a good work to be considered, and hopefully there will be some follow-up afterwards. Let's continue on investigating the use of this. Okay.
Sorry, can I ask one more question?
Thank you.
Sorry, can I ask just one more question?
Sure. Yeah.
It's a follow-up on the scaling of the number of samples, system size, and translation symmetry. Because when you explained that what was fine, the TFIM example, but I recall you also did an NBL case, and that case there's no translation. Right? So can you comment about the number of samples scaling with system size?
I see. Yeah, this one you would have the number of samples scale with the system size. Yeah, both in the width and the depth. Yes.
But when you scale with the system size, did you study the scaling that you need? Maybe is it linear, exponential?
It's linear. So this is like guaranteed by this theoretical upper bound here. Like this O of square root n t log t over ns. This is actually due to the fact that we're sampling like finite samples instead of like infinite samples, right? And you can see that the size of the PQC one need to use for like fixing the time slice, right? Fixing the time slice. It means you fix the depth of the circuit, so you only grow in the width. So the number of free parameters only grow linearly with the system size. So in return, the number of samples we find it's also like grows like linearly with system size. So okay, you want this thing to be a constant. So in order for the second term here to be a constant, you want ns to grow like as t log t, but t grow with n. So you small n, I mean, like so in return you want ns to grow as n log n. Yeah, so it's like roughly linear.
And that's not really, that's as you said, that's independent of the time, the depth, right? Or where does the depth come into play?
So you have to fix one thing, right? You either fix
okay,
that
right.
and fix the time. Let's fix time. Yeah. Like if you change time and depth at the same time and depth at the same time, then you're changing two things. But if you fix time, then yes, it grows like roughly linearly. The number of samples. So still quite efficient in my opinion. Yeah.
Right. Yeah, that sounds good. Yeah, but for the simulation result that you showed, you know, as it is a time evolution, right? I believe you were showing how the propagation of the or the localization of the charges. So that in that case, did you change the number of samples, or you basically use the same the largest one that you need for the longest time?
Yeah. We found that like for this system size, roughly for say total evolution time for like 0.5, you don't need that many samples. So
Okay.
you only need like a dozen samples roughly.
I see. And then you just use that number of samples and you could extrapolate the. I don't know if I remember correctly. This was when you was this the example where you studied a short sample of time and you extrapolate the evolution, or was this a different example?
Yeah. We train on a very small time, and we then extrapolate to long time limits.
I see. Okay. That sounds very interesting. Yeah, that's very good. Yeah, thanks for clarifying.
Yeah, no worries. Yeah, these are like great questions, I think.
Right. Yeah. And then thanks Yuxuan for staying first because it's kind of overshoot by quite a bit. And hopefully it's time. And thanks again for the very interesting talk.
Yeah.
And hopefully see you soon in person. And enjoy your stay in. And see you.
Yeah, thank you for the invite, and good luck on thesis writing and everything.